Lesson 28, Power Series. A power series about a constant A, or just power series, is any series that can be written in the following form, going from either n equal to 0 or n equal to 1 to infinity, of C sub n, which is a constant, times x minus a raised to the nth power. So if you expanded it out, it would be c times, say, x to the 0, c times x minus 1 to the first power, possibly whatever a is equal to. The c's are called the coefficients. And the first thing, and I'm just reading this courtesy of lamar.edu site, the first thing to notice about a power series is that it is a function of x. And that's different from any other kind of series that we've looked at to this point. In the prior lessons, we've only allowed numbers in the series, and now we're allowing variables to be in the series as well. Convergence is still a major question that we'll be dealing with, but since we have the variable x, then you may not have just one point of convergence. You may have an interval of where your series converges. And to help us find what's called the interval of convergence, we use the ratio test, and we know that the absolute value of x minus a is less than r. That's part of the ratio series test, and that indicates convergence. If r is 1, so if we had absolute value of x minus a is less than 1, then that would be the area or interval that our series converges. The number r, capital R, is called the radius of convergence, and it's pretty easy to find. You must have your absolute value in the form x minus a. If you have a constant in front of, or a coefficient in front of your x, like say 4, then you may have to divide or factor out of 4, but you need it in the form x minus a, absolute value of x minus a. So r is the radius of convergence, and the intervals of all x's, including the endpoints, if need be, for which the power series converges, is called the interval of convergence. And I'll show you in a few examples later how to find that particular part. Just a word of caution, when you get the interval of convergence, you have to test the endpoints. In other words, you have to plug each endpoint in for x and see if that makes the series converge at that particular value. Let's look at this first example. Determine the radius of convergence and interval of convergence for the following power series. So let me switch to my smartboard. Now on the next page, we use the ratio test. So a sub n plus 1 is all of this first part here. And the ratio test, remember, it's the limit as n approaches infinity of a sub n plus 1 over a sub n, where a sub n is your original series. Now, since we're dividing, this particular website already flipped the a sub n. So that's this part here. Now, a few things to note. -1 raised to the n plus 1 power can be broken down as -1 to the nth power times negative 1 to the first power. And the same is true right here. Sorry, it's kind of hidden. But x plus 3 to the n plus 1 power can be broken down as x plus 3 to the nth power times x plus 3 to the first power. And the same thing down here with the 4 raised to the n plus 1. It can be broken down as 4 to the nth power times 4 to the first power. We expand these terms out so we can cancel some common terms. So the 4 to the n's are gone. The negative 1 to the n's are gone, as well as the x plus 3 to the n powers. So we are left with negative 1 to the first power, or just negative 1, n plus 1, and just x plus 3. And that's all over. 4 is left, and just n. Now let's take the limit as n approaches infinity. And the x plus 3 we can pull out to the front because it's not going to be affected by the limit since it's in terms of x. Now, if we simplify the numerator, absolute value of negative 1 is still positive 1. So that just has n plus 1 over 4n. Now, to take the limit as n approaches infinity, if you have the same highest exponent, which we do here both top and bottom, then you take the ratio of the coefficients to get your limit. So our L, so to speak, is 1/4 times the absolute value of x plus 3. Now for a power series, because x can change, it's a variable, we need to determine the radius of convergence, or in other words, the kind of the perimeter where our power series can converge, and then also the interval of convergence. So we know from the ratio test that our absolute value, or our particular limit, has to be less than 1 in order to converge. Now let's get rid of the fraction by multiplying both sides of the inequality by 4. So that leaves us with now absolute value of x plus 3 is less than 4, excuse me. Well, we can immediately identify the radius of convergence, and our absolute value is in the proper format, x minus c or x plus c. So the radius of convergence is equal to 4. Now let's find the interval of convergence. So we had absolute value of x plus 3 is less than 4, I'm sorry. And you know from the property of absolute value inequalities, we can rewrite this as negative 4 is less than x plus 3 is less than 4. Now when we subtract 3 from all 3 parts, we get the interval negative 7 is less than x is less than 1. Now before we can declare this as our interval of convergence, we have to test the endpoints. We have to plug the endpoints into the original power series, because maybe one or both or neither of our endpoints may cause the power series to converge. Now, if we plug in an x and it causes the power series to converge, then we would have to make that a less than or equal to sign. If the x does not cause the power series to converge, then we leave it as just less than. So let's plug in -7 first into our power series. And I went ahead and did that for -7. So where I see an x, I plugged in -7. And that gave us -4 to the nth power. Now, -4 to the nth power, we can rewrite that as -1 to the nth power times -4 to the nth power. And that should be +4 to the nth power here in green. And the 4 to the nth powers cancel out. Now, the -1 to the n powers, we use the product rule for exponents. We keep the base -1 and add the exponents. So that would be -1 to the 2n power. And no matter what you plug in for n, it's always going to be multiplied by 2. So it would be squared to the 4th power, 6th power, whatever. And that's always a +1. So what we have here that we're taking the limit of is 1n. So when you plug in n, infinity for n, we still get infinity. So that means, according to the nth term test, the series diverges when x is -7. So that means our less than symbol for -7 stays the same. Now let's test x equal to +1. And what I'm doing is, where I see an x in our power series, I'm going to plug in 1. Alright, so that would give us just 4 to the nth power. And the 4 to the nth powers cancel out again. And when we take the limit as n approaches infinity of, well, what's left? -1 to the nth power times n. That gives us, if we plug in infinity, it's actually all going to infinity. It really will not exist per se. So if we let x equal to 1, it will make the power series diverge. So we don't use less than or equal to here for 1. It would just be less than 1. So from -7 less than x less than 1 is our interval of convergence.